Vector shows the movement of charge. Basically, it's a line from depolarized to non-depolarized cell, or we can say that it's a line from cells that have negative charge to cells that have positive charge. The magnitude of the vector is determined by two factors. First of all, it's the stage of depolarization or repolarization, and second, and the most important factor, it's tissue mass. It's important because the bigger is the vector that is sensed by electrodes, the bigger will be deflection from isoelectric line. To explain this, there are 8 cardiomyocytes, and we know that maximal vector is formed by the maximal difference in electric potentials. So in resting state, all cardiomyocytes have positive charge, and if first cell depolarized, the charge became negative, and at this stage the difference in electric potentials is minimal, so the vector of depolarization at this stage will be minimal. But if half of this tissue became depolarized and half is non-depolarized, the vector of depolarization became maximal, because the difference in electric potentials at this stage is maximal, and the maximal difference in electric potentials forms the maximal vector. Also, the magnitude of the vector usually depends on tissue mass. The bigger is the tissue mass, the bigger is the vector. For example, there are 8 cells, half of them depolarized and half is non-depolarized. In this case, there is a maximal difference in electric potentials with formation of the maximal vector for these 8 cells. In the second case, there are 16 cells, half of them are depolarized and half are non-depolarized, so there will be maximal difference in electric potentials with formation of the maximal vector for these 16 cells. And if we compare the maximal vectors for 8 cells and for 16 cells in this stage of depolarization, it's obvious that in the second case with 16 cells, the vector is bigger than vector in first case for 8 cells. So the bigger is the tissue mass, the bigger is the vector. Now we can discuss all the possibilities of interactions vector with electrodes and interactions between vectors. There is a lead that is formed by negative and positive electrodes, and below lead we see isoelectric line where electric activity that is registered by positive electrode will be depicted. If the vector is orientated parallel to the lead in the direction to positive electrode registers significant elevation from isoelectric line. If the vector is orientated parallel to the lead, but in the direction to negative electrode, active electrode registers significant depression from isoelectric line. If the vector is orientated perpendicular to the lead, active electrode will register just isoelectric line. There will be no deflection from isoelectric line. Another possibility is when vector is orientated under some angle to the lead. For example, in this case, active electrode will register significant elevation from isoelectric line. Because if the vector is located under some angle to the lead, active electrode will register only the projection of this vector on the lead. And it's obvious that the smaller is the angle, the bigger is the projection of this vector on the lead. And the magnitude of its vector projection is directly proportional to the deflection from isoelectric line. In this case, the vector is orientated to positive electrode. The projection of this vector is big, so elevation from isoelectric line will be significant. If the vector is orientated towards positive electrode, but under the big angle to the lead, in this case active electrode registers minimal elevation, because in this case the projection of this vector on the lead is minimal. So if the vector is located under the big angle to the lead, the projection of this vector is small, and active electrode registers this as small elevation from isoelectric line. But during cardiac electric activity there are a lot of vectors in different directions. So how vectors interact with each other and how electrode registers this? There is the principle of vectors addition. For example, if there is one big vector and one small vector, and they are both orientated in the same directions towards positive electrode, active electrode registers this as very high elevation from isoelectric line. Because for this electrode, the sum of these vectors is equal to vector 1 plus vector 2, because these vectors are both orientated in the same direction. And positive electrode registers the sum of these vectors as substantial elevation from isoelectric line. Elevation because the sum of these vectors is orientated towards positive electrode. Another example, there is one big vector that is orientated towards positive electrode, and second vector is orientated towards negative electrode. In this case, the sum of these vectors is equal to vector 1 minus vector 2, because these vectors are orientated in opposite directions. And in this case, active electrode registers elevation from isoelectric line. Another possibility is when vector 1 is orientated parallel to the lead towards positive electrode, and second vector is orientated under the angle towards positive electrode. First of all, how to calculate it mathematically correctly. So it's vector 1, it's vector 2. The resultant vector will be the diagonal of a parallelogram made from those two vectors. So we form parallelogram made from those two vectors, and the diagonal will be the resultant vector. And the projection of this resultant vector for electrode will be the sum of these two vectors. So basically for electrode, the sum of these vectors will be equal to vector 1 plus the projection of vector 2, because these two vectors are both orientated in the same direction, towards positive electrode, that register significant elevation from isoelectric line. But we can simplify this calculation because it's not necessary to draw the resultant vector to calculate how electrode will approximately register these two vectors on ECG. So again, it's vector 1 and it's vector 2, and because these two vectors are both orientated in the same direction, the sum of these two vectors is equal to vector 1 plus the projection of the second vector on the lead. So it's the projection of the second vector, and if we add this projection to the first vector, we'll get the sum of these vectors, that is registered by active electrode as significant elevation from isoelectric line. And if we compare a mathematically correct version with simplified calculation, basically for electrodes there will be no difference in the sum of these vectors. But for vector analysis on the XXL system, it's necessary to know the resultant vector and the principle of resultant vector formation. For example, the formation of the resultant vector of atrial depolarization, that is depicted on ECG as P wave. Atrial depolarization starts from the right atrium, so initial vector is located downwards and a bit to the left. And after left atrium begin to depolarize, and the vector of left atrial depolarization is located more to the left. And also this vector is bigger due to the greater tissue mass in left atrium. And to calculate the resultant vector of atrial depolarization, we make from these two vectors parallelogram and draw the diagonal that will be the resultant vector of atrial depolarization. It simplifies ECG analysis because if we know the normal orientation of resultant vectors, we know how in normal condition it should look like on ECG. So basically we know the normal morphology of ECG complexes, and also we can say why they became deviated in pathological conditions. For example, there we see the normal orientation of the resultant vector of atrial depolarization that on ECG is represented as P wave. So we can see that in normal condition, firstly it will register P wave as elevation from isoelectric line, because the projection of this vector on first lead will be orientated towards positive electrode. The same way AVF will register P wave as elevation from isoelectric line because the projection is orientated towards positive electrode. But the projection of this vector on AVR will be orientated towards negative electrode, and that's why AVR in normal condition register P wave as depression from isoelectric line. We call this negative P wave. And also we can see that AVR is basically the only lead that in normal condition will register the negative P wave on ECG. Again, it's because the projection of resultant vector of atrial depolarization, P resultant on this lead, is orientated towards negative electrode. Another example, if first vector is orientated towards positive electrode and second vector is located under the angle towards negative electrode. Again, from these two vectors we make parallelogram, and the diagonal will be the resultant vector. The projection of this vector on the lead is orientated towards positive electrode. From this picture we can see that basically for electrode, the sum of these vectors is equal to vector 1 minus the projection of vector 2. So we can approximately determine the sum of these vectors for electrode and say how electrode will register this on ECG without drawing parallelogram. And in this case we see that the sum of these vectors is orientated towards positive electrode, and positive electrode will register this as elevation from isoelectric line that will be proportional to the sum of these vectors.